A non-empty set G is a group. You could say this is our most important definition for the semester. A non-empty set G is a group if, first of all, there is an operation associated with G. If there is a binary operation on G, an addition or a multiplication, you might say. In general, in the abstract, we think of it as a multiplication. Should I write down like a dot for the binary operation? You could. We don't typically bother. Our textbook, and I mentioned this in the lectures, our textbook essentially takes this phrase, binary operation on G, to mean there is an operation, a mapping even, you could call it, that takes really an ordered pair of elements of G and maps it to an element of G. That's a way to denote the idea of a binary operation. Effectively, by assuming this, we're saying the operation is closed. The author doesn't use the word closure in the definition of a group, but effectively when the author uses the phrase binary operation, the author means it's closed. So what other properties does it satisfy? It's got to satisfy the associative property. AB in parentheses times C equals A times BC in parentheses for all A, B, C in G. Right, backwards E means there exists, upside down A means for all. Associative property. Over here, when you use parentheses like this, the idea is do A times B first, then multiply by C on the right. Over here, the idea is do B times C first, then multiply by A on the left. Notice I am emphasizing the words right and left. C is on the right here, A is on the left. It's important because in general, the operation is not going to be commutative. Just like matrix multiplication is not commutative. Property 2, there exists an element E in G. That is going to be the identity. AE equals EA equals A for all A in G. And property 3, for every element in G, there exists an inverse element. What does the inverse element have to satisfy? When you multiply A and A inverse in either order, you get the identity. This is the definition of a group. It is amazing. This is the astonishing part of the course, right? This should induce awe in you ultimately in the end, by a couple months from now, hopefully. It is amazing that this abstract definition has so many consequences. It is a very robust thing that has lots of interesting consequences. One consequence is that up to isomorphism, there's only one group with one element, only one group with two elements, only one group with three elements, but two groups with four elements. But back to only one group with five elements, two groups with six elements, one group with seven elements. I'm forgetting how many with eight. It's more than two, might be four. Maybe four group with eight elements. Back to two groups with nine. Turns out I happen to know, I believe this is right off the top of my head, even though And you might have noticed prime numbers 2, 3, 5, and 7. They're only one group in each of those cases. 255 is not prime, right? It's multiple of 5, for example. But there's only one group of order 255 with 255 elements. Our goal is to classify groups. We're kind of like mathematical botanists. And the idea of isomorphism, same form or not, is the key idea that helps us classify. And somehow the number of elements in the group helps us do that. But there are infinite groups as well. Z, all integers under addition, is a group. But it's got infinitely many elements. If you wanted to make its Cayley table, there would be infinitely many things to fill in. It would be an infinite matrix. I don't think I want to do that. The real numbers form a group. R stands for the real numbers, including all fractions, including all decimals, which includes all irrational numbers, like pi and e, the number e there. Square root of 2, blah, blah, blah. That's a group too. The complex numbers under addition is a group. I should have also probably mentioned in here the rational numbers. Q under addition is a group. Z is a German thing, Zahlen. For number, it represents the integers. R is the real numbers, just like the word real starts with R. C is the complex numbers. Complex starts with C. What about Q? Q is the rational numbers. Q for quotient. Fractions, where the numerator and denominator are integers and you're not dividing by 0. There are lots of examples of groups. This just barely scratches the surface. This is sort of just the most common examples. Zn, consisting of 0, 1, 2 through n minus 1, is a group under addition mod n. By the way, because every group is more than just a set, it also has the binary operation. Sometimes people will say, don't just call G the group, but call the group an ordered pair where G is the first element of the ordered pair and dot is the second element, where dot represents the multiplication. Okay, we're not going to do that in this class, but I wanted to just mention that some books do that. To emphasize, a group is more than just a set. It's a set with a binary operation, meaning it's closed and it satisfies these properties. Nowhere in here is the commutative property, though. Are there groups that satisfy the commutative property? Sure, we already saw some. When a group satisfies the commutative property, if AB equals BA for all A and B in G, we say, well, we could say G is commutative, but instead we say G is abelian with a capital A, because it's in honor of a person with the last name of Abel, starting with an A. I think he was Swedish. I think he was Swedish mathematician. Maybe Norwegian. I'm like a quarter Swedish, a quarter Norwegian, so I don't really care. But one of those two was from what Abel was from, lived a couple hundred years ago. When the group is abelian, we say, when the group satisfies the commutative property, we say the group is abelian.